Hello students, this is Mr. Allen, and today we are looking at section 12.4, which is on angle measures and segment lengths. Now it sounds like we have already done this, but remember in chapter 12 here we're focusing on circles, so we're not just talking about angles and segments by themselves. So to be more clear, our objectives are to find the measures of angles formed by chords, secants, and tangents, and to find lengths of segments associated with circles. So our first theorem today is theorem 1213, and it says that the measure of the angle formed by two intersecting lines inside of a circle is half the sum of the measures of the intercepted arcs. In other words, what we're talking about here is angle 1, if we want to know what angle 1 is. So what is the measure of angle 1? It is going to be half of the sum of the measure of arc x and y. So that's our formula here. So let's see that in an example. So here we're trying to find the value of x, and we can see that we have two intersecting lines, and we see that they intersect this arc and this arc. So that means that x is going to be 1/2 the measure of 30, oops, not 36, I'm not sure where I got 36, how about 46? Because this arc over here is 46 plus 90, kind of looks like a 6-2, that's a 90. So let's go ahead and add those together. So that's going to give us 1/2 of 136, and then 1/2 of 136, just to be extra careful here, is 68. So the measure of x, or the value, I guess, of x is 68. That was using theorem 1213. The key idea here is this angle is equal to 1/2 the sum of those two intercepted arcs. Now keep in mind that this point here is not necessarily the center of the circle. So this is not the center. It could be, but it's not in this case. All right, our next theorem, 1214. The measure of an angle formed by two lines that intersect outside of a circle is half the difference of the measure of the intercepted arcs. So this is actually almost a continuation of the previous theorem, except now instead of having the lines intersecting inside the circle, they are intersecting outside the circle. So again, let's go back to this first problem here. We have this line and this line intersecting inside the circle. So they intersected here inside of the circle. We're still doing the same thing. We've still got two lines that are intersecting. It's just now they're intersecting outside the circle. And by the way, here's the interesting piece. They could intersect at 1, 2, 3, 4 points. They could intersect at 1, 2, 3 points in the second example, or they could intersect just at 2 points. In other words, those are tangent. The theorem is very similar, except this time, instead of adding them, we're going to subtract them. Okay, so we have a very similar theorem to our first one. When they're intersecting on the inside, we add those intercepted arcs. But when they're on the outside, we subtract the intercepted arcs. So that's the only difference. It's very similar. It's actually almost just similar enough to be a problem, but let's just go ahead and see an example of that. So here's this one. This one's a little bit different. So we can see that we have two lines, or if you will, two segments that intersect outside of a circle. So we're now going to use theorem 1214. And here's our formula. And it tells us that the measure of angle 1 is equal to 1/2 x minus y, where x minus y are the measures of those intercepted arcs. Okay, so here is our angle 1, if you will. We'll call that the measure of angle 1. We'll call this guy here, I'll call that guy x. And then I'm going to call this guy over here, that's kind of the y in this formula. So now we're just going to put all of that into this formula. So what are we going to put in for the measure of angle 1? We're going to put 20. What are we going to put in for x? We're going to put in that 95. What are we going to put in for y? I'm going to put z. Now I should make a point here that I made z the smaller arc. And it maybe isn't clear, but I mean, I hope that it kind of makes sense. We want this value here to be positive, this 95 minus z. We want that to be positive because we need angles to be positive measures in general. And so anyways, that's why I made the 95 the x and not the y. So now we got this equation. How are we going to solve that? Well, the first thing I would do is multiply both sides by 2. So I'm going to multiply this side by 2, and I'm going to multiply this side by 2. And that's going to cancel the 1/2. And then so I'm left with 40 equals 95 minus z. And so then I'm going to subtract 95 on both sides. So that's going to give me negative 55 equals negative z. And then, of course, z then is going to be 55. So the value for z is 55. And again, we use theorem 12.4, which is right here. I'm sorry, 12.14. All right, let's look at another example. This one's kind of a more application example. So here we are looking at Earth. So we've got Earth here on the left. It says a satellite in a gyrostationary orbit above the Earth's equator has a viewing angle, the Earth, that forms 2 tangents to the equator. The viewing angle is about 17.5 degrees. What is the measure of the arc of the Earth that is viewed by the satellite? In other words, the question is, let me do this with a highlighter, is they want to know what's this arc measure? So this is kind of a challenging question because there's only one unknown, sort of. So we're going to be very careful with this one. So I'm actually going to go to a new slide here. We're going to use theorem. In fact, I should probably point that out because you see how these two lines intersect outside. So we're again going to use theorem 1214, which says that the measure of angle 1 is equal to 1/2 x minus y, and we're going to try to fill this in the best that we can. I'm going to move my picture here out of the way. Okay, so we know that the measure of the angle is 17.5, so that's nice. The problem is what are we going to do with this x and this y? So the bigger of the two, this is going to have to be the x. And the smaller of the two, I'll use a different color here. I'm going to let this here smaller one be y, okay? Because again, we want to keep that thing positive. Now the problem is the way I have it written right now is I still have 2 variables, so that's not going to make things get any better. But there's another restriction that we have to keep in mind, and that restriction is as follows. So follow me on this one carefully. We know that x plus y makes a full circle, so they have to add up to 360 degrees. So this is the key idea on this problem. Now what I can do is I can use the substitution property to actually substitute, and we're trying to find y. So I'm actually going to do x equals 360 minus y. Okay, so I can say that I can write x in terms of y. Now I have y, and now I have x. In other words, and I'm going to, you know what, I'm going to rewrite what I have over here because I'm going to need some more room. So I'm going to write 17.5 equals 1/2. What am I putting in for x? Well, this is x. So that's going to be 360 minus y minus, and what am I going to put in for y? I'm going to put y in. Okay, this is a subtle little problem here, but let's see if this hopefully works out okay. All right, so let's go ahead and solve this. So again, I'm going to multiply both sides by 2. I'm going to do 17.5 times 2. I'm going to use my calculator here just to make sure I don't screw anything up. And I'm going to get 35 equals, and of course, since I multiply both sides by 2, that 2 is now gone. And minus y is minus 2y. Now I'm going to do 35 minus 360. I'm going to subtract 360 on both sides. Maybe I'll show a little bit of work there. So I'm going to minus 360 minus 360. And that gives me negative 325 equals negative 2y. And last but not least is I need to divide by 2. So we're going to divide, not 2, by negative 2. And that's going to give us our final answer here. I think I'm doing this in purple. So y will be equal to whatever negative 325 divided by negative 2 is, which is 162.5 degrees. So the measure of this yellow arc right here is 162.5 degrees. That's your answer. Okay, so that was kind of a more clever problem. All right, last theorem. Myself out of the way here. Theorem 1215 says for a given point and a circle. Now, okay, now we're going to shift here. So far, both theorems we've dealt with have been dealing with measures of angles and arcs. Now we're going to do our second objective, which is measuring lengths of segments. So for a given point and a circle, the product of the lengths of the two segments from the point to the circle is constant along any line through the point. So in other words, if I take this length A, oops, let me put a highlighter on here. If I take this length here, A, with a highlighter, if I take this length A and I times it by this length B, that is going to be equivalent to this length C times this length D. Now here's where it gets tricky. So follow me carefully on this one, carefully on this second example and the third example too. This length W times this length X plus W is going to be equal to this length Y times this length Y plus Z. And then, of course, the same thing over here. Now, notice it has a T squared. We've got that T squared because it's going to be Y times Y plus Z is going to be equal to Y times itself, or I'm sorry, T times itself, so T squared. So this one is going to take a little bit of practice on your part, so please pay careful attention to this one. Now again, remember, we're not talking about angle measures anymore or arc measures. So let's look at this example. Which of our three does this example look like? Well, it kind of looks like this guy here, doesn't it? So that's what we're going to do. And let me just draw it for you using the highlighter again. Okay, let's do yellow. So I'm telling you that this length times the whole length will be equal to this length times the whole length. Okay, so I'm going to erase that now. So here we go. 6 times 6 plus 8 is equal to 7 times 7 plus y. So this is this middle theorem. And so there's our equation. Now we can go ahead and solve this. Go ahead and get back to the regular pen. So we are going to have 6 times 14 equals 7. I'll just leave the left side or the right side alone. This is a y. So we got to do 6 times 14. Again, I'm going to use my calculator to not make any careless mistakes. That's 84. Now I'm going to go ahead and distribute. So I'm going to get 49 plus 7y. Now we got a two-step equation, so we got to do 84 minus 49. Again, I'm using the calculator here. I get 35. Divide both sides by 7. So it looks like y is going to be 5. Divide both sides by 7. And I'm going to get 5. In other words, what I'm telling you, we can check our answer here. It should be, I'll do this in green, this is my check. That should tell us that 6 times 6 plus 8 should be equal to 7 times 7 plus 5. In other words, 6 times 14, which is 84, should be equivalent to 7 times 12, which is also 84. And so it works. All right, last example. Now again, we're going to be using theorem 12.5 or 12.15. So which of the three does this one look like? Well, this one looks like that third now. This one looks like the third one. So here's our formula. So it's this piece times this piece is equal to this piece squared. In other words, set it up. 8 times 8 plus 16 is equal to z squared. So that's going to be 8 times 24 equals z squared. 8 times 24 is 192. That's equal to z squared. The square root of 192 is a decimal that I don't want to mess with too much. So let's see here. 192. Let's see if 36 goes into that. Nope. 192. Let's see if 16 goes into that. Okay, 16 does go into that. Let's see if 64 goes into 192. Ah, it does. So this is interesting. So this 192, so z is going to be equal to the square root of 192. But that's the same thing as the square root of 64 times 3. And the square root of 64 times the square root of 3. So that gives us 8 square roots of 3. That's your exact answer for z. Or if you want the decimal was 13.856. So that's the approximate answer. And I think that is the end of the examples.